welcome back to our course on scanning microscopy. In last few lectures, we have been discussing on scanning probe microscopic technique, and in that now we are continuing on atomic force microscope. In the atomic force microscope, we have partly discussed on different components, particularly how the probe is fabricated, the cantilevers, probes, etc., has been fabricated. And today we will discuss on detection methods and the modes of AFM operation. In the modes of AFM operation, we will discuss on 3 different modes: contact mode, non-contact mode, intermittent contact mode or tapping mode, and also we will discuss on constant force mode, constant height mode. Let us begin with the simplest AFM schematics. Here you see we have a sample, and on which there is a AFM cantilevers which will scan over the surface, and the deflection of the cantilevers has to be detected by putting a laser beam on the back sides of the cantilever, and the laser light reflects to a position sensitive detector. So, in that detection mode there are different detection mode. Most of the time beam deflection mode is used, and in the beam deflection mode, as you see here, a laser beam is striking on the back side of the AFM cantilever, and then it is deflecting back to a position sensitive detector. Now, as cantilever go up and down, the beam position will go up and down in the position sensitive detector. So, with that we can measure how much cantilever is bending upwards or downward, and thereby knowing the height of the sample or topography of the sample across the surface. And now, in these cases, most cases, the AFM backsides is coated with a reflective coatings, either gold or aluminum. In case it has AFM to be operated in a corrosive medium such as KOH or NaOH, electrolyte or liquid medium, then one must coat the backside of the cantilever with a inert material such as gold. Otherwise, if it has to be operated in vacuum or in the air, it can be aluminum coating can work. Now, then after the position sensitive detector detects the position of the cantilever, it gives the information to the feedback electronics, and feedback electronics will note the position of the cantilever or how much cantilever deflected upwards in the direction. And we have a stage motion in the xy direction. Sample stage will move in the xy direction. It will keep on moving in the xy direction. At every places of the sample, we scan particular region and get a surface topography. And the requirements for this deflection or detection method are that high sensitivity of the detection system in the sub-angstrom region, because the height is normally measured in the AFM below 1 angstrom, and it could, because deflection of the AFM cantilever is in the angstrom region, angstrom range. Therefore, the detection system should allow the deflection system should allow the measurements in the sub-angstrom regime. And also the measurement method should not disturb the deflection itself and should not cause any other effect such as heating, and it should be easy to operate with minimum calibration. We have 4 different detection method. The beam deflection method that you have seen, which is most commonly used. We also have interferometry. In the interferometry, the back side of the cantilever act as a light source, and then the reflected light is split into two parts. And these lights the splitted light are passes through two different path lengths. They are passes through two different path lengths, and then again they are recombined to produce an interference pattern, and from the interference pattern we can know the difference of the path length, and thus knowing the displacements of the cantilever or position of the cantilever. And it is a very high sensitive detection process, but the instrumentation is little complicated, therefore, not very commonly used in the AFM. Moreover, here the calibration is very accurate, because the positioning can be detected by changing the wavelength of the light that is reflected from the back sides of the cantilever. So, in the sense of the preciseness is concerned, accuracy is concerned, it is very highly sensitive. On the other hand, instrumentation is complicated. We also have a piezo resistance detection method. In the piezo resistant detection method, a piezo resistive layer is coated on the cantilever surface, back side of the cantilever, and then this piezo resistive layer will change its resistance when mechanical force is applied to the cantilever. So, the resistance of the piezo resistive layer depends on the mechanical stress, and therefore, as the cantilever is deflected upward or downward, there is a mechanical stress on the piezo layer, and thereby change in the resistance. By measuring the piezo resistance, one can measure how much the deflection is occurring. So, which are directly proportional to each other. So, it is one of the process to also measure the deflection of the cantilever, but here signal to noise ratio is not as excellent as that of like optical methods. Compared to optical methods, it is not that high, it do not produce that high accuracy deflection measurements. We have a fourth kind of detection method, that is piezoelectric method. In this piezoelectric process, there are two electrodes, electrode 1 and electrode 2, and it is completely electrical process of measurements. It acts as a both sensor and actuator. To one of the electrode, we apply the converse piezoelectric process. We apply the variable voltage. When we apply the variable voltage, that will undergo deformation, and then in other electrodes we sense the changes of those reflection. Particularly, it is used in dynamic mode of atomic force microscopy measurement. Dynamic mode means when the cantilever is oscillated above the sample, and in this process this converse piezoelectric effect, by applying the variable voltage, we can make the cantilever to oscillate above the surface of the sample, and then we measure the resulting oscillation amplitude and frequency with other electrode. With one electrode's variable voltage is applied to make the deformation to the cantilever and thereby oscillation, etc. And with other electrodes we measure the resulting oscillation and resulting amplitude. From those one can know the position of the cantilever and thereby knowing the deflection by measuring the deflection. So, in this way one can measure, these are the four different way one can detect the cantilever deflection in the atomic force microscopy system. But as I told, the beam deflection method is most commonly used and most widely used in the atomic force microscopic technique to measure the deflection of the cantilever and thereby knowing the position of the cantilever, and that gives us the gap between the sample and the cantilever, thus providing the topology of the sample surface. Then, as you have seen in the schematic, we have a position sensitive detector to which light or the laser beam falls. In the vertical moments of the tip, in the vertical moment of the tip, the light will be moving upwards, or the laser beam will move in the upward z direction in the position sensitive detector, and we can measure how much upward or in z direction tip is deflected, and thereby measuring the distance between tip and sample. In other cases, if there is a bending of the tip, which will cause the horizontal movement of the tip, and therefore, the light, the reflected light on the position sensitive detector will move in the horizontal direction, and these horizontal movements or bending of the tip occur due to torsion or frictional force or lateral force. And this is this frictional force occur only when the tip is in touch with tip is in the touch with the sample, or sample and AFM tip are in contact with each other. And this will also allow us to measure the lateral force and frictional force of the sample surface by knowing the bending of the tip, how much bending occurs at which location, thereby getting information about the frictional force on the surface of the sample. If we look at the primary modes of operation, there are three primary modes. One is contact mode. As the name suggests, here tip, the AFM probe and sample are in contact with each other. They touch to each other, and therefore, they have to be closely spaced. The distance between tip or nothing but probe and the sample in these cases is normally less than 0.5 nanometer. Less than 0.5 nanometer separation between tip and sample, and when the tip and sample are very close to each other, then at that region there is a repulsive force. We have discussed the Lennard-Jones potential curve in our last lecture. As you see in this graph, the force versus probe sample separation distance concern, the force is increased, the repulsive force increased markedly when the tips and sample separation decreases, and in this region, this blue arrow region is the region where repulsive force predominates, and this happens when tip sample distance is close, very close. What I mentioned here, it is less than 0.5 nanometer. This is the contact mode. So, tip will be contacting the surface of the sample. Then we have another mode which is called non-contact mode. Non-contact mode is the mode where the tip and sample are little away from each other, but there is an interaction. There is a interaction between the tip and sample, and that is the region where attractive force predominates. Attractive force is the force when we have two objects very far away from each other, there is almost no interaction or negligible interaction or zero interaction. As we bring those two objects close to each other, then after a certain distance they will first have a attractive force predominating, and that is the region when the tip samples are away that much of distance away from this separation, we say non-contact mode, where attractive force predominate. As you see here in the Lennard-Jones force versus distance curve, this portion is our attractive force, and this region is our non-contact, this region at which tip sample separation are measured, or when the tip sample separation is in the attractive force region, then the measurement is called non-contact mode of measurement. Then between this contact and non-contact mode, in the middle portion, this is the region which is called intermediate or intermediate region, when the tip goes from attractive to repulsive region, or almost where there is no force of interaction to the repulsive region when the tip goes, then we say it is a tapping mode. In the tapping mode, tip, as you see here, tip is going close to the sample, that means it is going to the repulsive force region of the sample, and then it is going back upward where there is no force between the tip and sample, and when this tip goes backward and forward and backward above the sample, then we say it is intermittent contact or tapping mode of measurement. And here in the non-contact mode is when tip sample are far away from each other. Not far away means it is about more than 2 nanometer, and where attractive force predominates. Going detail, going little more, we can also differentiate these modes with two different categories, that is called static atomic force microscopic measurement, and another is called dynamic atomic force microscopic measurements. So, when the probe scans over the sample with oscillation, when the probe will be oscillating above the sample during the measurement, it is called dynamic mode of measurements. If the probe is not having an oscillation, then we say it is a static mode of measurements. And as in case of contact mode, the tip is in touch with the sample and it is not oscillating, therefore, it is called static mode of measurements or static AFM. On the other hand, non-contact mode and intermittent contact mode, where the tip will be oscillating above the sample, as it is oscillating, as it oscillates above the sample, then we say it is a dynamic mode of operation. And non-contact mode can have dynamic, can have static also. In some cases, static measurement is done, but mostly it is done with a dynamic mode of process. If we go to discuss a little more about contact mode, contact mode is operated in the repulsive regime of the force distance curve, and it is also called static mode, as tip does not oscillate above the sample and the sample is scanned in the xy direction, and when the tip sample gap is small, cantilever will sense the force and we can measure that force and use that force for the imaging purpose. And one of the important criteria for the contact mode of measurement is that the spring constant or force constants of the cantilever should be less than the sample surface. So, only when the spring constant of the cantilever is small, then only it will make deflection or it will bend properly to give us the deflection of the cantilever, that is telling us how much deflection occurs and the height of the height or topography of the sample. If that means it is supposed to be a small spring constant that is in the range of less than 1 Newton per meter, small spring constant, so that it should be deflected by the small force and also enough resonance frequencies not to be susceptible to the vibrational instabilities. Because when the spring constant is small, automatically the resonance frequency also gets smaller, because resonance frequency is also directly proportional to the spring constant, but that the probe should have enough vibrational enough resonance frequency such that it should not be highly susceptible to vibrational instability. This is the requirements for contact mode of measurement, and the contact mode of measurements is done again under two process. One is constant height mode and another is constant force mode. In the constant height mode, the tip is kept at a fixed height. Tip is kept at a fixed height and sample is scanned in the xy direction. As sample is scanned in the xy direction, as sample has roughness on its surface, at some places the distance between tip and sample will be closer to each other, at some places tip and sample distance will be away from each other, and therefore, the force will keep on changing when they are close to each other, tip sample close to each other and tip sample little away from each other, the force will no more remain same. By measuring the force, and the force will be measured by the deflection of the cantilever. When the force is attractive force, tip will be the cantilever will go downwards, and if there is a repulsive force, the cantilever will go upward. So, we will know, one can measure the deflection of the cantilever, and thereby from the deflection one can measure the force, and from that force we can create an image by which is directly related to the distribution of force across the surface of the sample. This is what constant height mode. As you see here in the left side, in the constant height mode, the z is fixed, the distance between tip sample initially put into a set value, and then sample is scanned in the xy direction, and there will be deflection of the cantilever due to the change in the distance between tip and sample, and from the deflection that z of the cantilever we can measure the force, and thereby plotting the distribution of force. In the constant force mode, this fz is fixed, and but sample is go up and downwards to measure a constant force. So, the deflection of the cantilever has to be kept constant. In the constant force mode, deflection of the cantilever remains to be fixed. In order to maintain that constant deflection, the sample has to go upward or downward while going in the xy direction, so that we can measure the constant deflection, and as sample go upward and downwards, we can measure the height of the sample. So, the same graph, similar graph you can get by plotting the z versus x in these cases, the height of the sample versus distance in the x and y direction. So, constant force mode provides same cantilever bending, and that is the interaction force, the force to be kept constant, that is why it is constant force. And to keep the interaction force constant, the feedback system changes the voltage applied to the z scanner. So, z feedback is on, here z feedback is on, and the change in the voltage, because feedback is given with a piezo materials here with the which is on the sample stage, and the change in voltage is proportional to the substrate surface topography. In this way, we can measure the surface topography or 3D image of the sample by using constant force mode. So, both the process give us 3D image, same 3D image. One can do by constant force mode, one can do by constant height mode. If we look at the advantage and disadvantages, this contact mode of AFM allows a faster scanning, it is very high resolution, because here tip is touching directly to the sample, therefore, it gives the maximum resolution among other modes of measurements in AFM, and but it is good for smooth sample. If the sample is not very smooth, then possibilities of tip scratching the sample surface and the tip being get damaged is high. So, in order to avoid those, one either has not to use contact mode, or one can only use the hard sample, because soft sample have more prone to get damaged. So, soft sample are not prepared to be measured by contact mode, because in the contact mode the tip may damage the surface of the sample. Moreover, as the tip is touching the sample surface, Therefore, we can measure the frictional force, lateral force of the sample surface that we cannot measure by other mode, like when tip sample are not in touch with each other. Disadvantages: force can damage the soft sample. Presence of lateral force can also distort the image. You will see later how it can distort the image. As per the application of the contact mode of AFM is concerned, certainly we can get surface topography with resolution, lateral resolution. This is a lateral resolution better than 1 nanometer, and vertical resolution is greater than vertical resolution. It will be around 0.01 nanometer. Vertical resolution is always higher in atomic force microscopy, and here we can directly determine the step height or thickness of the monolayer if it is a 2D material like that. So, note that in other microscopic techniques such as optical scanning electron microscope, helium ion microscope do not provide the step height quantitatively. So, in all other cases, if there is a step, indeed we will know there is a step here, but we cannot actually measure the height of these steps by other microscopic technique. Here is a image of contact mode AFM image of a rhodocene biomolecule. This rhodocene molecule is present in our eye to detect the dim light. As you see, the biomolecules can be directly imaged by the contact mode AFM image, and the resolution is quite good. In other microscopic technique, direct measurements, direct topology measurement or surface morphology measurements by of the biomolecule is not that simple and cannot be measured directly. Here is another example how this contact mode helps in measuring the step heights. These are the clusters of antimony island, antimony particle clusters on the MOS2 surface in the left side image, and in the B image you see a single zoom up clusters, and in the C you see here the height versus height curve or Z curve, telling about the height of these clusters, which is approximately 25 nanometer in these cases, accurately providing the height of these clusters on the surface, which cannot be measured by the other microscopic technique, including optical and electron microscopic technique. If we the contact mode of measurements goes with static AFM. If we talk about the parameters that are involved with dynamic atomic force microscope, there are several parameters that involves, particularly like this dynamic mode of AFM is used in non-contact mode and topic mode of AFM, and there this dynamic mode of operation involves several parameters that includes resonance frequency, force constant of the cantilever, and these two parameters are related to the cantilever, resonance frequency of the cantilever and force constant of the cantilever. The quality factor of the cantilever, it depends on the cantilever materials and also the environment. The driving amplitude, it is given, the oscillation amplitude is measured, driving frequency can be given, the phase difference between the driving and oscillation can be measured, and the frequency shift of the resonance shift relative to this sample interaction can also change. So, these are the important parameters of the dynamic atomic force microscope, which is used for non-contact mode and intermittent or tapping mode of AFM. So, we will discuss this in our next lecture. So, in conclusion, the beam deflection method of detection method is most common in AFM to measure the cantilever deflection, and in the contact mode of operation the tip sample force can be measured via the deflection of the cantilever. It can be done by constant height mode or constant force mode, and the contact mode of AFM operation allows to study the frictional force including the lateral force etc. And it is contact mode is fast and provides very high resolution image. These are the reference. Thank you.